Good morning, everyone. Welcome back. So let's start our second lecture. So in the previous lecture, we discussed about the speed of light. And we showed that for a wave, in general, there are three components: the source of the wave, the medium in which the wave propagates, and the observer. Okay? And we showed that for all other waves, the speed of the wave is defined relative to the medium. But for the for light, for E and M waves, because the medium, the E and M waves can propagate in vacuum where there is no obvious medium, the traditional picture runs into trouble. Okay? And last lecture we showed that the speed of light, the reference frame for the speed of light, cannot be the source because it violates the principle of locality and because it's also against the experimental results. Okay? So for the medium, traditionally people think that there must be a medium for E and M waves, and the speed of light should be relative to that medium, same as all other waves. However, that picture doesn't lead to anywhere. It leads to contradictory results where we need to keep adding new assumptions to this picture, to the physics picture, in order to fix all kinds of, in order to fit with experimental results. So this pathway doesn't seem to lead to anywhere either. So at the end of the day, where Einstein proposed that, how about let's look at the third option. Okay, no previous waves follow this option, but maybe E and M waves is special. Maybe the speed of E and M wave is actually defined in the reference frame of the observer. Okay, so today we will continue along the direction Einstein pointed out and ask the question: if the speed of light c is defined relative to the observer, what will happen? Okay. So in other words, if the speed of light c is defined in the reference frame of the observer, in other words, it means for all different observers, no matter in which reference frame this observer is, they will all get the same speed of light c. They'll all get the same speed of light. So this is the so-called invariance of speed of light in different reference frames. It basically means for observer, no matter which inertial reference frame we are in, we all get the same speed of light. Okay, so let's look at this picture and try to figure out what will happen. Okay, so because in this picture, we need to consider different observers. We need to consider observer in this reference frame and the observer in a different reference frame. And we need to show that they all give the same speed of light. That is our assumption here. Okay, we need to compare observer in different reference frame. So before we go into this physical picture of Einstein, we need to first figure out how to transfer from one reference frame to another. Okay, how to compare two different observers if these two different observer happens to be in two different reference frame. Okay, so before we go and discuss the physics, let's first look at what will happen if we transfer from one reference frame, from observer in one reference frame to another observer in a different reference frame, moving with a different velocity. Okay, so the transfer of a reference frame will be the first topic that we are going to discuss. Okay. And of course, at the end of the day, as you learn from undergrad to E&M, we know that Einstein theory leads to the so-called Lorentz transformation. Okay, Lorentz transformation keeps the speed of light invariant from one observer to another. Okay, in most E&M courses, people will just say, oh, because Lorentz transformation preserves the speed of light, and if Einstein wants the speed of light for all the observers to be the same, we have to follow Lorentz transformation. Okay. But if you really think about that, that argument is not quite a complete story. Lorentz symmetry preserves the speed of light, but it does not mean we have to follow Lorentz symmetry. How about maybe there is another transformation, not Lorentz transformation, a different transformation, also preserve the speed of light? Why not we follow the other one? Why do we have to follow the Lorentz transformation? Actually, it turns out there is a reason behind the thing. Okay, there is a reason behind this story. Okay. Lorentz symmetry is not only one transformation that preserves the speed of light. What we will show today, and also a little bit in the next lecture, is that Lorentz symmetry is pretty much the only possible transformation between reference frames that preserve the speed of light. Okay, so in order to prove that, in this lecture, we will first look at the transformation between different reference frames in general. Okay, we will not assume whether we have Lorentz transformation or Galilean transformation. We just ask the generic question. If we have two different reference frames and we want to compare measurement in these two different reference frames, what will happen? Okay, without assuming the speed of light is invariant in different reference frames, without assuming Galilean invariance, or without assuming Newton's law, and just ask the question, what is the most generic possible reference frame one can come up with? Okay, and the final conclusion of this section is this. Okay, so if we consider two different reference frames with relative velocity v, we assume this relative velocity v is along the x direction, as we will show later. Okay, then we can show that the coordinate in one reference frame, t, x, y, z, and the coordinates in the other reference frame, t prime, x prime, y prime, z prime, must follow this transformation. Okay, so that is the final conclusion of this section. We will prove that mathematically, this is pretty much the only option we can have if we consider a generic transformation between reference frames. Okay, this transformation is very similar to the Lorentz transformation. Okay, but it's not the Lorentz transformation. This one is more generic. So Lorentz transformation has a very specific gamma, which we'll discuss later. Okay, Lorentz transformation, we know the gamma depends on speed of light, depends on velocity. Okay, here the gamma is arbitrary parameter we can tune. Okay, for different transformation between reference frames, we take different value of gamma. If the gamma happens to be the Lorentz transformation gamma, then we get Lorentz transformation. If gamma is 1, this transformation is actually the Galilean transformation. Okay, so any transformation between different reference frame must take this form. Of course, with certain assumptions, which we'll discuss slightly later. Okay, so this is the generic transformation between reference frames. And in the next section, we will show that if we start from the most generic possible transformation, and then assume speed of light is the same quantity, is the same value for different observers in different reference frame, then we will get Lorentz transformation. Okay, so this is a more generic one. And next section, we'll discuss the Lorentz one. Okay, so in this section, we will show you that regardless of the details, the transformation between reference frame always take this structure. Okay, so how do we know that? So first, let me demonstrate. Let me list out the assumptions and the conventions we have. Okay, so this section is about the assumptions we will assume and the conventions that we will follow. So assumptions and conventions, they are related, but there is also a fundamental difference between them. Convention means that we choose some setup. Okay, this setup we don't have to choose that, but we can always follow this convention. Okay, and assumptions is we don't really know, we can't really prove whether it's right or not, but let's assume that is right, and for some reason we think it's probably right. Okay, so convention is not assumption. Convention is just something we choose to use. Okay, so for example, let's here consider two reference frame. One is this blue reference frame. The other one is this red or yellowish orange colored reference frame. Okay. Let's assume the relative velocity between these two reference frames is v. Okay. So if we think the blue one is stationary, then the red one is moving to the right with velocity v. Okay. If we are in the red reference frame and say the red frame is stationary, then the blue one is moving to the left with velocity v. Okay. So their relative velocity is v. So the first convention we will do is that we will set up two coordinates, okay, two spatial coordinates. One for the reference frame k, which we call the k is the blue one. The other one is k prime, which is this red one. Okay. And we will take the convention such that at time equals 0, the two reference frames have the same origin. Okay. We'll assume at t equals 0, the two reference frames have the exact same origin. And t equals 0, the origin of the red frame and the origin of the blue frame coincide. Okay. If they don't follow this convention, if we have at time t, the origin of the blue one is here, the origin of the red one is here, then we just choose a different xyz coordinate. We shift our definition of xyz coordinate. Because we believe our universe is homogeneous, choosing the origin here and here or there doesn't matter. They will all lead to the same physics. So we can always follow this convention such that at t equals 0, the blue and the red coordinates have the same origin. X, y, z equals 0, and x prime, y prime, z prime equals 0, and time 0. Okay. Of course, for time not being 0, let's say if we wait a little bit, the origin of the blue one and the origin of the red one were separate, okay, because they have relative motion, they have relative velocity between each other. But at t equals 0, we can always choose the two origin to be the same. So that's the convention that we will follow. And the second convention we will follow is about the directions. Okay, we will choose the convention such that both the k and the k prime frame, the x direction is along the direction of the velocity. Both of them has x direction along the direction of the velocity. Okay, so this is also a convention we can choose. Okay, we can choose x direction to be any direction in this universe, but here we will choose x direction to be parallel to the velocity v. That's the second convention. Okay. And the third convention, okay, we will choose that the y and the z coordinate, y and the z axis for the k frame, and the y prime and the z prime axis for the k prime frame to be parallel to each other. At least they should be parallel to each other and t equals 0. Okay, so they should be parallel to each other. That's the third convention. These three conventions can always be followed as long as we choose the right coordinates. Okay, these are not assumptions, it's just how we set up our coordinates. Okay, now the next, we will discuss some of the assumptions. Okay, the first assumption that we will assume is that the coordinate transformation between one reference frame and another is a linear transformation. Okay, linear transformation means t prime, x prime, y prime, z prime. That's a coordinate, space-time coordinate in the second reference frame, and t, x, y, z, the space and time coordinate in the first reference frame, are related by a linear function. Okay, with linear terms and also possibly some constant terms. Okay, linear term and constant term. We don't allow quadratic term, cubic term, or quartic term, or any higher order term of t, or x, or y, or z. Okay, so this is assumption. This assumption, of course, is not something we can really rigorously prove. Okay, we cannot mathematically prove this. If our universe happens to choose a linear transformation between different reference frames, that's fine. But if our universe chooses to have a nonlinear transformation, that's not something we can mathematically prove or disprove. Okay, so here we will take this linear transformation as assumption. Okay, so as I said earlier on, this linear transformation is not something we can rigorously prove that our universe must do this. But this linear transformation has we have some reason to believe our universe probably will follow this. Okay, the reason is because the linear transformation makes things a lot easier and a lot simpler. Okay, if we have a nonlinear transformation between reference frame, then there will be a problem. The problem is about the homogeneity. Okay, we know that our universe is homogeneous. At least we assume our universe is homogeneous. Every part of the universe, actually we do the experiments here, or we do the experiment on Mars, we follow the same physics law, fundamental law. Okay, so the space, the whole space is equivalent here and any other point. Okay, so that assumption means everywhere the space point is equivalent. Okay, so for a linear transformation, if we assume the space t, x, y, z in one reference frame is homogeneous, okay, every single point follow the same physics law, then after a linear transformation, one can prove that in the new reference frame, every single point will still follow the same physics law. If it's a nonlinear transformation, then it's typically not the case. Okay, well, if it's a transformation is nonlinear, then even if in the original frame, k frame, say t, x, y, z, all the physics laws are the same everywhere, then after the transformation, when you do a nonlinear transformation to go to a different coordinate, the physics law cannot remain the same. Okay, one example to demonstrate this is, say, let's draw a grid, some horizontal lines, some vertical lines. Let's draw a 2D grid. Okay, if we draw a 2D grid, say this is t, x, y, x, y, z coordinate. In the t, x, y, z coordinate, we draw a 2D grid. Okay, then we do a transformation to go to the t prime, x prime, y prime, z prime coordinate. Okay, if this transformation is a linear transformation, if we draw a grid which is homogeneous, so every square in the grid has the same area, after linear transformation, we can show that all the squares, all the plaquettes still remains the same area. Okay, they are still homogeneous. But if this is a nonlinear transformation, some of the plaquettes will become larger, some of the plaquettes will become smaller, and the different plaquettes will have different shape, everything changes. Okay, so before the transformation, everything is homogeneous, but after a nonlinear transformation, the system does not remain homogeneous anymore. If we want our universe, our space to be homogeneous in every reference frame, the transformation better to be a linear transformation. Okay, this linear transformation guarantees that if it's homogeneous in one reference frame, the other reference frame will also say, oh yeah, the universe is homogeneous. Okay. So that's the hidden assumption behind this linear transformation. Okay. We assume our space is equivalent, every single point is equivalent, and we assume in every reference frame, they're always equivalent. So that requires the transformation to be a linear one. Okay, so for linear transformation, we know from linear algebra, this linear transformation can also be written in this matrix form. Okay, so this is a 4x4 matrix. This column vector is t, x, y, z, the four-dimensional coordinate for frame k. This is the four-dimensional coordinate for frame k prime, and they have a linear relation. This is a linear term, and it's possible to have some constant term also. Okay, and this constant term happens to be 0 because of the first convention we chose. Okay, we chose this convention when t, x, y, z are all 0. T prime, x prime, y prime, z prime are also 0. Okay, so if t, x, y, z is 0, this guy is also 0, which means this b must be 0. Because of the convention we chose, this b term is gone. Okay, so from the convention and the linear transformation assumption, the transformation generically looks like this. Okay, so generically, this is what this transformation will look like. And here we only utilize one assumption, that is the transformation is linear. Okay, so that's the first assumption. So the second assumption that we are going to assume is the so-called isotropic assumptions. Okay, so we assume our universe is isotropic. So in terms of coordinate, this means we have the freedom to choose x, y, z, the direction of the orientation of the x, y, z direction. Okay, the x, y, z direction, we can choose them to be any direction as long as they are perpendicular to each other. All the physics law should remain the same. Okay. So if we come back to our frame transformation problem, okay, the transformation between different reference frame problem, we have a k frame and a k prime frame. Okay, so here in this coordinate system, x direction is uniquely determined due to our convention 2. Okay, so in convention 2, I said that I want the x direction for both k and k prime frame to be along the velocity direction. So we know the x direction. But the direction of y and z, or y prime and z prime, it's not fixed. Okay, I can choose, in this figure, I choose up direction to be y, and this direction towards me to be z. Okay, so this is x, this is y, and this is z. But I don't need to choose this y, z direction. If I rotate everything along the x-axis, choose z direction to be here, and y direction to be here, and z direction to be down, it also works. Okay, so we have the freedom to rotate the coordinate system along the x-axis. But due to convention 3, the convention 3 says y and y prime need to be parallel, z and z prime to be parallel. Due to convention 3, I know that if I rotate the y-z axis, I should rotate the y prime, z prime axis at the same time. Okay? But as long as I rotate the y-z axis and the y prime, z prime axis by the same amount around the x-axis, everything should remain the same. Okay? So mathematically, this rotation along the x-axis is described by the rotational matrix. Okay, we know the rotational matrix looks like this: cosine, cosine, sine, sine with a minus sign. Okay, and this cosine, cosine, sine, sine term mix up y and z. It's mix y and z because we are rotating around x along the x direction. We are mixing y and z. Okay, and x direction and the time direction remains invariant. So they're both identity along the diagonal. The t and x remains invariant. Y and z has the rotation. Okay, and we need to do the same thing for the k prime frame. Okay, we need to do the same rotation for the k prime frame. And the isotropic, if you assume the universe is isotropic, after this rotation, everything should remain the same. Which means after this rotation, this matrix should remain the same. Okay, we shouldn't be able to tell any difference, no matter we choose this is yz or this is yz, this is yz. They should be all equivalent. So they should have the same transformation matrix for my coordinate transformation or for my reference frame transformation. So this assumption 2, our universe is isotropic, enforce some constraint on this rotational transformation, as we will show later. Okay, and the third assumption is the so-called mirror symmetry. Okay, so this mirror symmetry here we assume in our universe, anything happening in our universe, the same thing will happen in the mirror in their mirror image. Okay, in other words, if we take a video of some physical procedure and then take a mirror image and show this video, I will not be able to tell whether this is original video or it's actually the mirror image of original video. They all follow the same physics law. Okay. So this mirror symmetry are also known as chiral symmetry, because under a mirror transformation, the chirality of object will flip. Okay. So here we will consider a very specific mirror symmetry. That's a mirror plane parallel to the YZ. Okay. So we put a mirror plane parallel to the YZ, and in the mirror image, the first thing will happen is K and K prime frame flip. K become K prime become K. The reason is because the K and the K prime frame, their relative velocity is V. Okay. So if we assume the K frame is stationary, then the K prime frame will be moving towards the right with velocity V. But if we put a mirror in the YZ plane, in the mirror image, the K prime frame will be moving towards the other direction, towards the right. Okay. So the mirror image flips the relative direction, flips the direction of the relative velocity between the two frameworks, the reference frames. Okay. So if the relative direction, relative velocity is flipped, this basically means K and K prime frames is swapped. Okay. K becomes K prime become K. Okay. So that's basically what the mirror does. Okay. So first of all, mirror swap K and K prime, the two reference frame, because it flips the sign of the relative velocity. And secondly, it flips the sign of the x coordinate. So x becomes minus x. Okay? So if we combine these two effects together, this is what happened under a mirror image. So under a mirror image, the prime coordinate becomes the coordinate with no prime. The coordinate with no prime becomes the coordinate with prime. This is because K and K prime frames, they switch, they swap the two reference frame under mirror. And on top of that, we need to flip the sign of the x coordinate under this transformation. Okay, so this is a mirror transformation. And under this mirror transformation, the coordinate transformation should remain the same. That enforces another constraint on this 4x4 matrix. Okay, if we combine these two, this constraint together, we will come up with a universal structure of the reference frame transformation. Okay, so here, the next section, I provide the outline of the proof, not the detail. The detailed proof will be shown in the next section, okay? So basically, the first assumption tells us the transformation need to be a linear transformation, okay? So we can write down the transformation between two reference frames in this matrix formula, okay? And this is the first assumption, along with one of the conventions we adopted in the earlier part of the previous lecture. The first assumption tells us it must look like this. Okay? I don't know exactly the value of these metric elements, but it must have this structure. A second assumption tells us this matrix should remain invariant under the rotation along the x-axis, under this transformation. Okay? And if that is true, this metric cannot be an arbitrary metric. It must take the following structure. The off-diagonal component must be 0. The diagonal component can survive. And more importantly, for the lower right corner, the two off-diagonal components here need to take opposite sign. Okay, so that's the only way to make sure the matrix is invariant under rotation along x-axis. And that is the only way to make sure that the space is isotropic. If the transformation matrix does not take this form, then we will be able to tell that some y direction is special and some z direction is special, and rotate it will give you different physics. Okay? That's against the assumption of isotropic universe. Okay? So the isotropic, assuming the universe is isotropic, tells us transformation must look like this. Okay, that's the second step. And the next step, also that's the first step, using the rotational symmetry to determine the structure of the transformation. It looks like this. And next step, a second step, is to utilize the mirror symmetry. Okay? We also mentioned early on, if we assume our universe is the same as its mirror image, everything should be invariant. Everything should stay the same under this mirror transformation. Okay? And under this mirror transformation, if we want the matrix to remain the same, we can prove that this matrix must take this structure. Okay? And this structure is actually even more specific than what we got before. Okay, so this is what we got from the rotational symmetry, and if we combine rotational symmetry with also mirror symmetry, also apply mirror symmetry, the transformation matrix must look like this. Okay. So first of all, the lower right corner must be identity matrix. Okay. With just rotational symmetry, we don't really know what this is. We only know these two off-diagonal components need to take opposite sign, but we don't know their value. But if it's also has mirror symmetry, then it must be 1, 1, 0, 0 identity matrix. Okay. The upper left corner, previously we don't know what these four values are. Any value would obey rotational symmetry. But if I want both the rotational symmetry and the mirror symmetry, this upper left 2x2 block must take this specific form. Okay, so the diagonal component, this guy and this guy must be exactly the same. If they are not exactly the same, the mirror symmetry will be violated. Okay, by looking at the image of our universe and its mirror image, we will tell they are different. Obviously, this is our universe, this is mirror image. That should not happen. So these two values need to be the same. Okay, and similarly, the off-diagonal components, they are not the same, but they are related. Okay, they are related by this specific relation. They both contain a quantity A10, but this component actually also has a coefficient A00 square minus 1. A00 is the diagonal component. Okay, so that is our that is the outline of the proof. So for the detailed proof, the full proof, this will not be required. If you are interested in this, you can read this section 1.23, where I show the specific step-by-step how to utilize this symmetry and the symmetry transformation to prove that this matrix must take this form with rotational symmetry, and then must take this form with the mirror symmetry. Okay, if you are interested in the detail, you can read the next section, which is optional reading section, and this section you can see all the details. How do we prove it must take this form? Okay. So for the bottom line, okay, as long as we assume the transformation of coordinate, the transformation of reference frames is a linear transformation, which better to be true, otherwise we will not have a homogeneous universe. Okay, we assume it's linear, and if we assume all different directions in our universe are equivalent, isotropic, and if we assume mirror image and the true physical system looks exactly the same, the so-called chiral symmetry. If you assume these three symmetries, these three assumptions, the transformation between two reference frame must take this structure. Okay, so that's the second step. So finally, there is still a cosmetic procedure we need to do. Okay, that is our third and the last step. Okay, so in general, from all the three assumptions, we showed that the transformation matrix must look like this, and we have only two free parameters. One is A00, another one is A10, and A00. Okay, that's only two free parameters we have here in this coordinate transformation. Okay, and we can realize that first of all, the ratio between A10 and A00, the ratio between them is just the velocity, the relative velocity between these two reference frames. Okay, that's something quite easy to realize, and the details you can find it in the next optional reading section. Okay, so the A10 and the A00, their ratio is velocity with a minus sign. Okay, and secondly, A00, this A0, the diagonal component, we don't know its value, but it's never hurt to just give it a name. Okay, instead of calling this one A00, we will call it gamma from now on. Okay, so A00, we call it gamma. Okay, for A10, because A10 is minus velocity times A00, so A10 is just minus velocity times gamma. Okay. Now velocity is known. The relative velocity between these two reference frames is known. So the only freedom we can choose here is gamma. Okay. After this procedure, we come up with the transformation I showed you earlier, this transformation. Okay, from one reference frame to another reference frame, regardless of details, as long as we follow the three assumptions we have mentioned earlier on, the transformation must look like this. Okay, and this transformation contains two control parameters. One is velocity, v. Okay, that's the relative velocity between the two reference frames, and the other one is gamma. We don't know the value of gamma. Okay, so the gamma in principle can take any possible values, and all of them, any possible value are allowed, And all of them will satisfy the assumptions we have earlier. So in order to determine the value of gamma, we need to introduce some additional physics. Okay, so the symmetry itself does not pinpoint the value of gamma. We need to introduce some additional constraints. Okay, for example, if we assume in Newton's mechanics, one important assumption is all reference frames follow the same time. They all have the same time. Okay, when we do the reference frame transformation, things changes, the coordinate changes, but the time never change. If time remains unchanged, when we transfer from one coordinate to another, then it means t prime need to be equals to t. If we want t prime to be equals to t, there is only one possible gamma can give you that. That is gamma equals 1. Okay, so gamma equals 1 is the only possible transformation between reference frames that satisfies all reference frames share the same time. Okay, if you assume all reference frames share the same time, gamma has to be 1. And if gamma is 1, you can easily check this. When gamma is 1, this is just a Galilean transformation. Okay, so Galilean transformation is actually not an accident. It's one of the specific option for this generic possibility. Okay, so generically it must look like this, but if you assume different reference frame at the same time, gamma has to be 1, and if gamma is 1, we have Galilean transformation. Okay, and now with Einstein, okay, so with Einstein's assumption, Einstein said, okay, let's assume speed of light is defined in the reference frame of the observers. In other words, all observers need to all have the same speed of light. That gives us another constraint on this transformation. In other words, that gives us another constraint on this gamma. And we need to figure out what that gamma is. That is the next section. Okay, so let me summarize before I go to the next section. Okay, so in this section, we discuss the most generic transformation between two different reference frames. Okay, and here we made 3 assumptions. The transformation is linear. It's better to be linear, otherwise the universe cannot stay homogeneous. And secondly, this space is isotropic. Okay, and thirdly, we assume our universe has a so-called mirror or chiral symmetry, or so-called parity symmetry in particle physics. Okay? And with these 3 assumptions, one can prove that the transformation has to look like this with the unknown parameter gamma. Okay? And to determine the value of gamma, we need to assume some additional physics, and Newton or Galilean assume time remains invariant under the coordinate transformation, under the reference frame transformation that gives gamma equals 1 and Galilean transformation. And Einstein is considering a different setup. Okay, so I will skip the optional reading section. If you are interested in, you can look at it. Okay, it's mainly some linear algebra stuff and the matrix multiplication stuff, and it's basically just mathematical proof, and there's nothing significant on the theory on the physics side in this section. Okay, so this is the optional section. This ends the optional section. As you can see, the proof itself is quite long, but it's just some mathematical details, nothing very important on the physics side. Okay, now let's look at the speed of light again. Okay, as I mentioned earlier on, Einstein said, let's consider the third option. Maybe the speed of light c is defined relative to the observer. Okay, in other words, for any observer, no matter what reference frame he or she is in, when he or she measures the speed of light, they will all get the same value. They will all get c. Okay, and that leads to the so-called Lorentz transformation. Okay, so in this section, we will start by this generic coordinate transformation we assume. Okay, where I say this must be true. This coordinate transformation must be true, and then we say, is there possible we can choose some gamma such that the speed of light remains c for any observer. No matter how I change my reference frame, the speed of light c does not change. Okay, so that is as you all know, that leads to the Lorentz transformation. Okay, so how do we know that? So first, let's start from this generic transformation between two different reference frames, and I don't know what the value of gamma is yet. Okay, then let's assume in reference frame k, txyz is the coordinate of reference frame k. Okay, that's our first observer. Okay. In reference frame k, let's assume on time t, there is a light source at the origin. The origin is y equals x equals y equals z equals 0. Okay. Now this light source emits E and M waves, or emits a photon, or emits light. Okay. And this light, of course, it propagates, it moves, at the speed of light c. Okay. Then after a little bit, and time t, this light signal should reach distance x squared plus y squared plus z squared equals ct. Okay. So we wait a little bit, and this wave reached point x, y, z. And this point x, y, z, the distance between this point and origin is x squared, y squared, z squared. And the time it takes for the light to travel from origin to this point is t, and their ratio is speed of light c. Okay. So for the reference, for observing this reference frame k, it will get this speed of light c. Speed of light c means x squared, y squared, z squared square root distance divided by the time it takes for the signal to travel this distance is c. Okay, that's the first observer. In other words, the first observer will find this. Okay, ct, t is the time, ct is the distance it traveled. So the square of the distance traveled minus the square of the distance traveled. X squared plus y squared plus z squared is the square of the distance. This should be 0. Okay, it's the same thing, same formula, written a slightly different way. Okay. Now let's look at a second observer. For the second observer, he will also see at t equals 0, t prime equals 0, at origin, there is a light signal. Okay, it sends out a light signal. This is because the convention 1 we choose in the previous section. Okay, we chose the convention and time equals 0, both reference frame have the same origin. Okay, so it's the time 0 for the origin of the first reference frame, and the second reference frame also have the same origin are the same. So for the second observer, we will also find at t equals 0, t prime equals 0, there was a light source at origin, and this light source sent out a signal. And then after a while, say after time t prime, this light signal reached a point x prime, y prime, z prime. Okay, and this t prime, x prime, y prime, z prime, and the t x, y, z has a relation. That's just the reference frame transmission. Okay, so the x, y, z and the t, the point where this signal is traveled to. Now after the reference frame transmission becomes this. Okay, if we know x, y, z, t, I can get x prime, y prime, z prime, t prime. And from the point of view of the reference frame k prime, reference frame k prime will also think the speed of light is c. Okay, although we have a transform, although we are now in a different reference frame, this reference frame also thinks the speed of light is c. If the speed of light is c, then again in this reference frame we have the same formula. Okay, the numerator here is the distance the light signal traveled. The denominator is the time it used, t prime. This ratio should be c. In other words, we have this formula. Okay, the speed of light square times t prime square, that's the distance, c times the time square, the distance square, minus distance square should be 0. Okay, so this is k prime frame gets speed of light c. In the k frame, we also get speed of light c. We have the same speed of light, that's the assumption of Einstein. And we know the tx, yz and t prime, x prime, y prime, z prime are related by this generic transformation we discussed earlier on. Okay, it's better B. And so we can replace this t prime, x prime, y prime, z prime by the transformation. Okay, so we replace t prime by this guy. We replace x prime by this guy. Y prime and z prime is just y and z according to the transformation. Okay. So we replace t prime by this guy. So we get this term. We replace x prime by this transformation, this term. We get this one. Y prime, z prime just become y and z. Okay. So in the k prime frame, this combination need to be 0. Okay. So we rewrite this speed of light definition in k prime space back into the txyz coordinate. Okay. And okay, so this, and we know this combination must be 0. Okay. And now let's look at this y and z. Okay. If we are back in the k reference frame, in the k reference frame, we know this guy is 0. Okay. Or in other words, this guy is 0. That's the same thing. Okay. This equation tells us y squared plus z squared y squared plus z squared, mass equals to x squared minus c squared t squared, x squared equals to c squared. Okay, so y squared plus z squared is related with t and x, and that's a relation. Okay. And in this equation, as we can see here, there is a y squared, there is z squared. So we can replace this y squared and z squared by this guy. Okay. Substitute this yz by t and x. Okay. After that substitution, this equation becomes this guy. Okay. So there was yz here. Now there's no yz anymore. I replace yz by t and x. Okay. And the first two terms remain the same. I didn't do anything for the first two terms. Okay. Now we can, massage this formula a little bit. We can rewrite this formula in the next structure. Okay. This structure tells me, actually in this structure, I have a t squared term with some coefficient. I have an x squared term with some coefficient. And I have a tx term with some coefficient. Okay, so we have three terms, each of them has some coefficient. And this guy needs to be 0, regardless of the value of t and x. Okay. If I want this guy to be 0 for any t and x, I must make all the three coefficients to be 0. So this coefficient needs to be 0, this coefficient needs to be 0, this coefficient needs to be 0. Okay, so I have three equations, all these three coefficients need to be 0. So I have three equations here, but I only have one unknown, that's gamma. Gamma is the only thing I don't know here, okay? Three equations and one unknown, in general, there's no solution. You can't satisfy three equations with just one unknown in general. But it's very lucky. For Einstein's assumption here, these three equations happens to have exactly the same solution, okay? So if we set gamma equals to speed of light divided by speed of light square minus v square, velocity square root, if we set gamma to be this value, all these three equations satisfied at the same time. Okay, it's very lucky. This assumption really worked out. Okay. Einstein's assumption, indeed, it turns out it worked out. Okay, and as long as we choose the gamma to be this value, our transformation preserves the speed of light. And if you take the gamma to be this value, this is so-called Lorentz transformation. Okay, so this is the story behind the Lorentz transformation. So the reason Einstein knows Lorentz transformation must be right if the speed of light is relative to the observer. Einstein knows Lorentz transformation is right if we assume the speed of light is relative to the observer. He knows this is because that's the only option. Okay, as we showed early on, unless our universe is not homogeneous, or our universe is not isotropic, or our universe break the parity symmetry, break the mirror symmetry. Unless those things happens, this is the only option. There's no other option. Okay? So most textbook tells you, oh, Lorentz transformation satisfies velocity. Satisfies the Lorentz transformation will preserve the speed of light in different reference frame. So it must be right. But logically, that's not right, right? One transformation satisfies speed of light invariance does not mean we have to follow the transformation. We could have other transformations give you the same physics, right? But actually, the real story behind Lorentz transformation is that there's no other possibility. There's no other transformation can achieve the same goal. Okay? Lorentz transformation is the only transformation we can have if we want the speed of light to be the same for different observers. If we want to have another transformation to achieve the same goal, then we need to break some of the assumptions we mentioned earlier. We need to assume our space is not homogeneous so that we can get a nonlinear transformation, or we need to assume our universe is not isotropic, etc. Okay, so Lorentz transformation is the only option. Okay. That's part of the reason why Einstein is so confident about his theoretical prediction. Okay. It's not a random guess. It is pretty much the only option allowed by mathematics. Okay. It's the only logically self-consistent theory. Okay, so this is the Lorentz transformation. And the gamma, now we know the value of gamma. Okay, so yeah, no, this is the gamma. Okay, so before we go to, before we conclude today's lecture, I want to mention one more thing, okay, about the feasibility of Einstein's assumption, the Lorentz transformation. Okay, so as we mentioned earlier on, Einstein assumed speed of light is relative to the observer, and if we follow that assumption, we come to the conclusion the transformation between different reference frames must be the Lorentz transmission, and gamma must take this structure. Okay, so logically that is self-consistent. So mathematically there's no contradiction. The theory does not have contradiction with itself. But logically correct and the self-consistency does not prove this is the right physics of our universe. Our universe, for right theory, it has to be self-consistent, but self-consistent theory is not necessarily the right theory for the universe. Okay? We could have some self-consistent theory, but it happens that our universe don't follow that theory. Our universe chooses to follow different theory. Okay? And in order to know and in order to check Einstein's theory at least is not obviously wrong, we need to do one more thing. That one more thing is to show Einstein's assumption does not go against any existing experiment. So here, existing experiment, I mean the experiment existed in the early 1900s when Einstein came up with this. Okay. So when Einstein came up with the theory of special relativity, Newton's mechanics and Galilean transmission has been studied for hundreds of years. Okay. So thousands of experiments, including the moving of apples, moving of point-like objects, and dreidels, or the moving of stars, planets, thousands of experiments, thousands of experimental observations proved that to very high accuracy, Galilean transmission and Newton's mechanics is right. Okay. Now Einstein is proposing something new, something different from Galilean transmission. Then at least what we need to check is this new proposal is not against existing theory, which proves Galilean transmission is very accurate. Okay? And we need to check that. Okay? And in order to check that, we need to first notice one thing. As I mentioned to you earlier, Galilean transmission basically means gamma is 1. Okay? And Einstein said, no, gamma is actually not 1, gamma is this value. We need to make sure that this value must be very close to 1, at least for all the experiments that existed before Einstein's time. Okay? So before Einstein's time, people did lots of experiments and always find gamma to be very close to 1. So we need to make sure that Einstein's theory is consistent with those. And indeed it is. Okay? From this gamma Einstein proposed, a Lorentz transmission, we can see that if the velocity of our reference frame, with this v, is very small. Small here means much smaller than the speed of light. Now, if v is much smaller than the speed of light, the denominator is approximately c. c over c is 1. Okay? So when velocity is small, indeed, gamma becomes 1, and it recovers Galilean transmission. So basically, the bottom line, Lorentz transmission, at least when velocity is small, it recovers Galilean transmission. So for all the existing experiments before Einstein's time, because the measured velocity, the velocity of the reference frame is always small, gamma equals 1 is always a good approximation. Okay, so this is at least a sanity check. Einstein's theory is not crazy. Okay, so to demonstrate this, let me give you an opposite example. Okay, if Einstein come up with assumption and then come up with a conclusion that gamma equals to 2, okay, then we know we don't need to spend any time to think about this theory. That theory is totally wrong. Okay, because numerous experiments has demonstrated gamma equals 1, or gamma at least is close to 1. If you come up with a theory that gamma is 2 everywhere, that is totally against the existing theory. It cannot be right. Okay? The reason Einstein's theory is right is because it modified gamma, but it does not significantly modify the gamma. At least when velocity is small, gamma goes back to 1, goes back to the Galilean transmission. Okay, so the bottom line from the lesson of special relativity, 2 things we learn. Okay, the first thing we learn is that for any physics principle, even if it has been verified by numerous experiments and accepted by everyone as fundamental doctrines, if there is some reason to think, to believe they might be wrong, we can question them. We can question any fundamental theory. For example, the Galilean transmission. Galilean transmission has been taken as granted for hundreds of years. No one questioned that, and hundreds or thousands of experiments prove it is right. However, when it's necessary to question it, like in special relativity, we question it. Okay? We say gamma may actually not be 1. Okay? That's one side, one lesson we learn. And on the other hand, The other side of the story, the other side of the lesson we learned is that when we question a fundamental physics principle, which has been verified by numerous experiments, when we question such a fundamental principle, we cannot make a new theory that is not compatible with that conventional theory. The new theory we come up with must be at least compatible with the existing one. So in special relativity, we need to come up with a new theory. This new theory, when velocity is small, gamma need to go to 1. Gamma cannot go to 2 when velocity is small. Okay? This is because the existing principle has been verified to very high accuracy by hundreds of experiments. Okay? If you come up with a new theory which says all those experiments is wrong, the experiment result decides everything. Okay, it's against the existing experiment, so those theory cannot survive. So we should be brave enough to question existing theory. But when we question existing theory, we need to make sure that the existing experiment supporting existing theory still survives within this new framework. Okay, so this actually here I want to mention again the example I mentioned in the previous lecture. Like about 10 years ago, there was an experiment reported from Italy about particle that a neutrino moving faster than the speed of light. Okay, so to question Einstein's theory, we need to have the bravery to do that. Okay, that's good side. However, for that particular experiment, the reported velocity of neutrino is way too high. It's way too high to be consistent with other existing experiments. For example, neutrino oscillation. Okay, if the speed of neutrino is beyond speed of light for some neutrino, where the other neutrino travels at the speed of light, they cannot couple. There's no way we can have oscillation between different neutrino species. Okay. Anyway, so if we try to modify a theory, but the step is too big, we show the existing theory, and the experimentally verified existing theory is totally wrong. Then it's most likely this new picture is wrong. Okay, so for that experiment, because the reported speed of light is too high, it's actually against the existing knowledge, existing other experiments, against the thousands of other existing experiments. So that guaranteed that results cannot survive. Okay, we still have a little bit of time left, so I will discuss one more topic before we dismiss today. Okay, so here we will revisit intuition about space-time. In other words, we'll revisit the basic intuition about the kinematics. As I mentioned in the last lecture, kinematics describe how is about how to describe the motion of an object without worrying about what is a cause, what is a force. Okay, so in kinematics, basically it's a description of space and time, the position of particle and time t, velocity of particle and time t, acceleration of particle and time t, etc., without asking what caused this acceleration, what gives the velocity of the particle, etc. Okay, and dynamics, the opposite of kinetics is dynamics. Dynamics discuss about what caused the motion. For example, Newton's second law, force induced acceleration. Okay, so in this section and in this chapter, we're all focusing on kinematics. Okay, as I mentioned and just mentioned, kinematics is all about space and time. How do we understand space and time? Okay, so our intuition and our basically physics picture about space and time mostly come from our daily life. Okay, so from our daily life, we have time, we keep track of time, and we keep track of distance we travel, distance we walk every day, etc. Okay, but Einstein told us some of our naive intuition about space and time is actually wrong. Okay, and how much of our existing knowledge, how much of our existing intuition from our daily life can survive in special relativity? Which part of them we should throw away? Okay, so that is the important question for the understanding of the special relativity. Okay. So here, this section, let me address that, and we will utilize some of this principle later. Okay. So the bottom line, as long as we are staying in the same reference frame, we don't need to worry about this. Okay, everything, all our conventional intuition and all our conventional knowledge we get from our daily life about space or time should still survive in special relativity. General relativity is a different story, but in special relativity, our convention and our traditional intuition about space of time also survives, as long as we stay in the same reference frame. But when we transfer from one reference frame to a different reference frame, our conventional intuition about that transformation need to be modified according to Lorentz transformation. For example, traditionally, we will say when we transfer from one reference frame to a different reference frame, the time remains the same. We can still use the same clock. And the Lorentz transformation and Einstein's special relativity tells us that's wrong. On the other side, the opposite to that, as long as we stay in the same reference frame, everything we'll know before, everything we learn from our intuition survives. Okay, so that's a very important principle. Lorentz transformation only impacts our transformation from one frame to another. If we stay in the same frame, there should be nothing different from conventional Newton's mechanics. Oh, so sorry, from conventional kinematics of Newton. The dynamics, of course, is very different. We'll discuss that in the next chapter. But in terms of space and time, as long as we don't change reference frame, everything remains the same. So let me demonstrate this with a simple example. Okay. So in this simple example, we consider two objects, A and B, or two persons, A and B. They initially were separated by some distance L. So let me draw a picture here. Okay. So this is person A, and this is person B. Initially, they separate by distance L. Okay. Then they start to move towards each other. Okay. They start to work towards each other. Person A is working with velocity VA. Person B with velocity VB. They're trying to meet together in the middle. Okay. And the question is, how long does it take for these two persons to meet in the middle point? Is it somewhere in the middle? Say they meet at C, point C eventually. Okay. So how long does it take? I will show you two ways to solve it. Okay. So firstly, the first method to solve this is that a method without changing the reference frame. We stay in the same reference frame. Okay. So here in this method, we say, oh, let's say time t. It takes time t for these two persons to meet. Okay. And in time t, person A traveled VA times t. Person B traveled VB times t. Okay. And the distance traveled by both these two persons added up together should be VA times t plus VB times t. And that should match L. That should be match the separation between them. And when this equation is satisfied, that's when they meet. Okay. And by solving this equation, we got T equals L over VA plus VB. That's the solution. That's how long it takes for these two persons to meet. Okay. In Newton's mechanism, in Newton's theory, okay, or in Newton's picture, if we describe the same kinematics, there is another way to solve the same problem, utilizing frame transformation, transform to a different frame. Okay. So that is, we can do this. So instead of using the ground reference frame, let's go to the reference frame of A. Okay, let's look at a reference frame of A. From reference frame of A will say, okay, I am not moving, but B is moving to me, towards me, with a velocity VA plus VB. That's the Galilean transformation. Excuse me. Because B is moving towards me with velocity VA plus VB, and initially we have the separation of L, time it takes, it should be L divided by VA plus VB. Okay, so in Galilean system, in Newton's theory, these two methods works equivalently. Both of them are right. Okay, but if we are doing special relativity, the first method is still right, because the first method does not involve reference frame transformation. We are staying in the same reference frame, and we are calculating distance. We are looking at distance in this reference frame, measure time in this reference frame, velocity in this reference frame, and everything in this reference frame. So our conventional knowledge still survives. Okay, but the second method in special relativity is wrong. We can't use this in the second. We can't use the second method. This is because second method involves transformation from one reference frame to another. If we have transformation from one reference frame to another, we can still do it, but we cannot use our conventional wisdom. Say, velocity transformation is VA plus VB. That's totally wrong. We need to rethink this according to the Lorentz transformation, and using the velocity transformation for Lorentz transformation, and using the length transformation for reference frame transformation. After reference transformation, we know length also change. Okay, and also equivalently important is time. When we transfer from one reference frame to another reference frame, the Lorentz transformation tells us time is also need to be modified. When we keep track of everything, we still will get the right answer. But this naive picture, this naive intuition, this velocity, addition of velocity, those things is wrong. Okay, so the second method cannot be utilized anymore. If we want to do this, we want to transfer to a different reference frame and do this calculation, we need to follow carefully the Lorentz transformation. Okay, but if we are using the first methods without reference frame transformation, staying in the same reference frame, our basic knowledge we learned in physics 101, or we learned in middle school, or even elementary school, all of them survives. Okay, so the bottom line, as long as we stay in the same reference frame, all our concepts about space of time still is correct. But once we want to change from one reference frame to another, we need to be very careful. Okay, so that is something we're going to discuss in the next lecture. So in the next lecture, we will summarize the non-trivial effects from Lorentz transformation and its impact on kinematics. Okay. Finally, one important note, all the discussions here is about kinematics. Okay, nothing related with dynamics. If we're talking about dynamics, even if we don't transfer to another reference frame, special relativity tells us the dynamics is different from Newton. Okay, our conventional knowledge, conventional understanding about dynamics, Newton's law is no longer right. Okay, we need to modify that. But if we just thinking about kinetics, just describe the motion of the object without asking what causes motion. For kinetics, as long as we stay in the same reference frame, everything remains the same as Newton. Okay, I think this is a good point to end today's lecture. So let me summarize. So today's lecture, we didn't discuss much new knowledge. Okay, so the most of the knowledge about Lorentz transformation, etc., you already learned it as undergraduate in your undergraduate courses. Okay, so today what we did is to revisit the Lorentz transformation and try to go a little bit deeper. Okay, it turns out the Lorentz transformation is not some random transformation Einstein happened to pick. It is a transformation that we have to pick if we assume the basic assumption about the universe, as I mentioned earlier. Okay, it's not an optional thing. It has to be right if we assume speed of light is the same for all observers. Okay, so that is the story behind the Lorentz transformation. So in the education or in the teaching about special relativity, one major confusion is that where does this everything comes from? Why this randomly written down transformation actually is the fundamental law of our universe? Well, hopefully through today's lecture, you will notice, you will realize that this Lorentz transformation is not a randomly written down transformation. There is a fundamental reason behind the thing, and we almost have no freedom to choose this transformation. If we want the theory to be logically self-consistent, this is pretty much the only theory we can write down. Okay, I think this is a good point to stop. And in the next lecture, we will continue our discussion about kinematics, and we will continue our review about kinematics. And afterwards, we will discuss about dynamics and how to describe physics laws and how to make physics laws satisfy the Lorentz symmetry and satisfy the Lorentz transformation. Okay, and I will see you next time.